Hi, everyone. My name is Chris Freeman. I'm a senior content engineer at Alteryx, and for the last 6 months, I have pretty much lived and breathed SparkR, and one of the primary contributors to the DataFrame API in SparkR. And I'm going to be talking to you about how this came about, how it's implemented, and the kind of things that we hope that you'll be able to do with data frames once you get your hands on SparkR, which actually was just recently released. So what are we going to talk about? Well, first off, we'll give a little introduction about SparkR in general, although I know you've probably heard quite a bit about it at this point. And we'll talk about the history of data frames and SparkR specifically, and some of the challenges that came about in trying to develop it. And then also the motivation for why data frames in general, but specifically why there's such a benefit in SparkR. And we'll go on to talk about how they work. We'll do a demo of some of the features of the data frame API. And then we'll talk about the things that are coming up, and hopefully you guys will have questions at the end, and I'll be happy to talk about them. So first off, what is SparkR? So by now you probably know SparkR is the new API in Spark 1.4. It's an R language API for Spark and Spark SQL. And the point of it is to expose existing Spark functionality, primarily the data frame API, in a way that is friendly to our users, that makes heavy use of our syntax and our data frame syntax. Much like the other APIs, it has a shell version, which you can activate directly from within Spark. But you can also import it as a package, just like you would any other package, and use it in RStudio interactively. So, but really, SparkR is an opportunity to make Spark accessible to our users who are already familiar with their own ideas and workflows about how to do predictive, how to program predictive workflows in R. Since R is such a widely used language for predictive analytics, it only made sense that we would want to take Spark and make it something that people could pick up and work with. So the other benefit is that by adapting it heavily to the R syntax, we don't have to ask our users to learn a new programming paradigm to work with Spark, but they can take advantage of all of the features that Spark has to offer. So SparkR initially began as just an R package. It was kind of a third-party thing, and it ported Spark's core functionality over to the R language, so primarily just RDD-based operations. And when I got involved, we realized that the next logical step was to work with schema RDDs and to add Spark SQL and the SQL context, all of that stuff, into SparkR so that people could start to hopefully work with more structured data in a way that was somewhat easier. So the initial implementation was the SQL context and schema RDDs. And cool guy that I am, one night I was browsing through the GitHub source code for Spark, and I noticed something. I noticed this. Pull request for data frames, and I thought that was really strange because as far as I had heard, this was back in Spark 1.2, there were no such things in data frames as data frames in Spark. And this was kind of a shock, and I thought to myself, oh, okay, well, I just got the SQL context and the whole schema RDD architecture into SparkR, committed it, things are going great, we're moving along. What's this data frame thing about? So I dig into the code, and I look at Reynolds commits, and I see this. Deprecated. Schema RDDs. No longer the thing. Data frames are what's coming around.
Yeah, we're running off the backup now. All right.
Okay. And so, yeah, deprecated. So this was me upon seeing this, because I had just spent quite a while trying to figure out schema RDDs only to find out that there was a brand new thing. And this is how I imagine that Reynolds probably looked over on his side. And now I know that probably wasn't the case, and he had the right intentions, but that's about how I felt. But then I thought, okay, well, maybe this isn't such a bad thing. So when I was first learning Spark and trying to just figure out how to do it, I decided the best way to do it would be to try and figure out how to do something simple. Just something that anyone would do who was working with data. And in this case, that was, I have some data, and I want to take the average of a single column. So I sat down and tried and figure it out. And this is what I came up with, right? So we read a text file in. We're going to flat map a string split function onto everything to split the rows into things that kind of resemble columns. And then we're going to map a conversion function to turn that second element in everything into an actual number so that we can do math on it. And then we're going to use reduce to pass an additive function so that we can reduce and get the entire sum. And then we'll calculate the average just like you would any other way. And this was my face upon realizing that you actually had to do all of this to get the sum of a column. And I just thought, there's got to be a better way. Like, there's no way that this is how it has to be. And it turns out that I'd had a vision, and also Spark had a vision, and everyone knew that this was not the way to do things like sum columns. So what I would have liked to see is I read in some structured data, and all I have to do, read it in. I can tell it it's JSON, it knows what to do, and it has some metadata already associated with it. And then I just have to do something that looks quite a bit like dplyr. I select it, I tell it which column I want to do and what I want to do to that column. And it turns out that that's exactly what you'll be able to do once you get into SparkR. So then the question is, why data frames? So data frames are kind of the best of both worlds, right? They use the whole distributed, parallel memory abilities of Spark that RDDs used to use, but they put a schema on top of it. We get metadata, we get column names, we get data types. We don't have to worry about converting things so that we can do basic operations on them. And that makes things much easier. It's much easier to get at certain columns, to do aggregations, to take the data, blend it, manipulate it, and get it to the point where we can do something predictive on it. And it's a natural extension in R because R already uses data frames. It's just the common language and everything. And it provided a very unique opportunity because while data frames as a construct are great across all of the languages, R has been doing this for a while, and there's a whole lot of stuff that you can do in R and a whole lot of workflows that already exist in R that we could take advantage of with the new data frame API. So to put it more succinctly, why data frames? Well, you get super awesome distributed collections. You get schemas that give you metadata, structure, and you can write declaratively instead of imperatively. Some magic happens, and then of course, profit. So in data frames in SparkR are architected in such a way that we have essentially two layers. So there is a system of S4 classes in R, which are basically R's object-oriented system. And they represent an actual class in R. It's a formal class that has its own methods, and you can use it to extend existing R methods as well as create your own, and do different types of method dispatch based on what kinds of arguments you have going into the function call itself. We also have a SparkR backend that lets you pass things in R to the JVM and back. And the reason that that's crucial is because SparkR is actually, while you have this formal data frame with its own methods, its own data, you're actually interacting with the JVM the entire time. And you get to use Spark and let the Scala side of things essentially handle all of the heavy lifting. To use the data frame API that's already there, but use the OO programming in R to really extend it and allow for a lot of different R syntactic sugar type things. And we also have a set of helper methods written in Scala to allow for, I guess, some simpler things about collecting to R data frames, manipulating the data in such a way that we can deal with some of R's quirks when going back and forth to the JVM. So the question is, why does that matter? Well, having native R classes allows us to extend the data frame API quite a bit by adding a bunch of different syntactic things that allow R users to start to interact with data frames in a way that will feel very familiar. But the fact that ultimately they're tracking and creating objects on the JVM and building out a DAG just like you would in regular Spark means that we get to take advantage of all of Spark's existing capabilities. We can take advantage of the catalyst optimizer, things like predicate push down to data sources, code generation optimization at the compiler level, a lot of things where sometimes you're writing a giant query and you can just reliably say, you know what, I'm not sure if this is the best way to do it, but let's let Catalyst handle it, and quite frankly, it will. So some of the data frame features in SparkR are that you have column access using either the $ or bracket operators, which will be very familiar to anyone who's used to working with R data frames. But we also have data frame manipulation methods that are very similar to dplyr, which is kind of the de facto standard for a lot of predictive work in R. And it has things like filter and group by, same things you see in the regular data frame API, but also things like mutate, arrange, and summarize that work just like they would in regular dplyr. And they also give us this the structure of SparkR also gives us access to other packages in R that make things a little bit easier. And you'll see what I mean by that in the demo, which is coming up. Although that begs the question of how do we switch back to my computer? All right, perfect. So, all right. All right, so in data frames in SparkR, you have access to a lot of the same data frame things. So you can create a Spark data frame from a regular data frame. Here we're using the canonical iris data set that just comes packaged with R. And all you have to do is call create data frame on it. And because data frames already have their own metadata inside of R, SparkR just infers that, creates a Spark data frame, and builds the schema for you. You can also create raw data, so much like you might create an array of rows in regular Spark, you can create a list of lists in R and pass them through to a schema where you create struct types with the metadata that you like to include, and it'll combine the two into a data frame that exists in the Spark cluster. But more to the point, you can also read out of an external data source. So in this case, we're reading JSON, and we're going to take some demographic data. So let's say we have an actual real-world problem to solve with SparkR. This would be the first part. We read in demographic data. It's organized by customer ID. We already have it structured somewhere, but we want to get it into Spark. So we load it, and it comes in, reads the schema, and boom, there we go. We get data organized by customer ID with some of the different categoricals that we'd like to include. So some of the basic data frame operations are like the column and bracket operators like I had shown before. For anyone who's used R, this will look really familiar. You can use the $ to select different columns, and actually if you use this in RStudio, which is a really popular R IDE, the way that the OO side in R is architected, the $ will actually give you tab completion in RStudio. So even though you're talking about an R or a Spark data frame, you can tab complete on different column names, which is actually purely by accident. Shivaram and I had no idea that was going to happen. But it turns out when you design things to follow R conventions, you get a lot of accidental benefits like this one. You can also use bracket notation to select multiple columns at the same time, and this is also very similar to our syntax. And you can create new columns either by modifying the data frame in place with the $ operator, or by using mutate, which is kind of a port from dplyr and follows its syntax, if you'd like to more formally add a new named column. And here you can see we've calculated petal and supple area by just creating new columns with the calculation in each of them. And just like in R, you can drop columns very easily. All you have to do is assign that value to null, and suddenly petal area disappears. Similarly, you can do things like you would see in the regular Spark data frame API, where you can filter on a pattern, you can filter on any number of conditions, but here you can see we're combining filter, we have our data frame, our demographics data frame, and we just call like on the pattern that we'd like to match on, and we only get the people who are in the age 40 to 44 group. And you can count on another condition. So similarly, you can do where, give it some kind of category, and you get to count everyone who lives in the Pacific. So the other thing is that you also want to do aggregations typically. And aggregations already exist in Spark, but we wanted to extend the dplyr methodology to aggregations, which involves group by and summarize. So here you can see we've loaded up some transaction data. So it's the same customers from before, but if you notice, the customer IDs repeat, right? So this is transaction data, meaning that it's not measured at the per customer level. But since the idea is that we want to prepare this data and get it into something that we can actually pass into a model, we need to first aggregate this before we can combine it with the rest of our data and make something of a training set. So what we do is we use group by and summarize. So we call summarize first, and we pass in a group by function that'll group everything on customer ID, specify the names of our new columns, and what functions we'd like to perform on them. So we're going to get transactions by counting the distinct number of transaction dates per customer, and we're going to get spend by summarizing or by summing the total outlay for every customer across all of their transactions. And we get a nice aggregated data set like this. Similarly with joins, we can select things, pass in a join right here, and then select the fields that we'd like. And we're able to join all of our data together in one very easy syntax. But let's say that we want to do more than just one step at a time. And we want to start adding things, and we don't want to have to assign variables every single time, because I hate assigning variables to every single step of my workflow. Well, we could pass in the join into a select, into a mutate, calculate our transactions above average here by passing in the expression itself and mutating the data frame so that we get that as a result, like so. But the thing is, in R, the one thing that's really annoying is that you have to nest all of your functions. And anytime I've ever talked about SparkR with anyone, they always ask me, where's the chaining operator? Where's something that lets me make pipelines? And it turns out that another really cool benefit of the way that SparkR was designed was that we found out that you can use Magritter, which is a very common R package that allows for pipelining Lambda functions and basically designing workflows in R that are much more intuitive and much easier to read because you don't have to read the function calls from the inside out. So if we look at that same one, we see now that the percent and arrow is the pipe operator. And instead of having to nest every function inside of the next one, so really we're starting with join, then we go to a select, then we go to a mutate. Instead, we can pipe the data in, call our join, do our select, and then inside of a Lambda function, we can actually calculate the average as a locally namespaced variable, and then pass that into mutate without having to do the entire calculation inside of the mutate. It makes it much easier to read, and the ability to use Lambda functions means that you can suddenly start to do a lot of transformations on your data frames in place without having to worry about having some unbelievably unreadable series of functions, but also not having to assign every single thing to a variable and possibly pollute the namespace. So as I was playing around with this, I realized that, all right, well, since everything in R is a function and method calls are all tied to functions instead of objects, and this is what Magritter takes advantage of, there's probably something else we could do. And it turns out that there is. You can make data frame pipelines. And this isn't an official Spark term, this is just what I'm calling it, but the idea is, now we have our data, right? So let's say we were trying to predict, a customer behavior. We have customer data like income and spend and transactions, and we have their demographic data, and we're almost there, but now we have some sample data where we know that some of our customers actually have been sent some kind of flyer or something, and we want to know how they responded to it. Well, the natural thing to do would be to join that data to the data we have, and then create a training and a test set. So in this case, we'll read in our sample data, and you can see all we have is customer ID and a respond variable. There's only 2,000 people, whereas the original data was 20,000. So what we want to do is join the two together and figure out who fell out of each side of the join, and then we have our training and testing set. Well, normally you would have to assign each of those and calculate, the filter. If you wanted to do the intersection, that would be an inner join, then you'd have to turn around and do a left outer join to get the people who didn't actually coincide in both data sets, and that would be your testing set, and the training set would be the full intersection. But in this case, since Magritter works so nicely with the way SparkR is set up, we can go ahead and do that join once, pass it into a Lambda function, do our different filters, and then using R's global assignment operator, which is just this double arrow, we can force the variable assignment up out of the Lambda namespace into the global namespace, and in one workflow create multiple data frames that we can now go back and reference. So here you can see we've created train DF and test DF based on different filter conditions. And when we come down here, now suddenly in the global namespace, we have two different data frames, which makes a lot of things more simpler when you're getting into really complex workflows, because I hate repeating myself in code, and I hate having to assign all these different things and repeat the same function calls. But being able to pass things into Lambda functions and nested Lambda functions means that suddenly you get one workflow that outputs all the different pieces that you need, and you're ready to go to move on to the predictive part. Okay, so can we go back to the other? Yeah. So what's coming up in SparkR? Well, on the roadmap, as you know, Spark 1.4, SparkR became official, and it's primarily focused on just the data frame implementation. In Spark 1.5, we want to start bringing in the predictive capabilities. As you know, SparkML is getting really popular, and the data frame API is becoming kind of the norm across all of Spark. And our goal in Spark 1.5 is to extend it to include machine learning capabilities. And if you want to see more about the future of that, there will actually be a talk in the data science track, I believe, at 4:30 about the just high-level roadmap for SparkR. In addition, we'll be integrating SparkR into Alteryx. So Alteryx provides like a drag-and-drop GUI for data analysis. So it lets you do all sorts of things from data transformation to geospatial analysis to predictive work, and it has a native R integration, which means that it's a natural partner for SparkR as it exists. So the idea here would be that you could have Alteryx on your desktop, you could interact with something using a drag and drop interface, interact with the Spark cluster remotely without having to use Spark Submit, and more importantly, without having to install the JVM on all of your analyst computers. And you can combine local and in-database calculations, including things like filter pushdown, into one workflow without having to worry about loading data into the cluster, out of the cluster, back and forth, and how you're going to mix them all together. You can just easily mix them together, and Alteryx figures out the mechanisms for you. So for the developer community, SparkR actually originated at UC Berkeley's AMP Lab, and has since picked up contributors from Alteryx, Intel, Databricks, and since it's come into Spark officially, it started to grow, and the number of contributions has increased. And one of the next things we're working on is integrating with Spark packages. So you may have seen that there's actually a Spark packages repo already that provides extensions for different language-specific APIs, as well as different data sources, or machine learning algorithms, or any other kind of features that you might want to add to Spark. And we really want to get that integrated with R because there's so much work already being done on all sorts of machine learning algorithms that we want to make it really easy to continue to extend SparkR without having to suddenly commit into Spark. And it would allow for a lot of modularity in terms of using SparkR because you wouldn't have to suddenly build SparkR in Spark with all of the different machine learning algorithms. You could go to the Spark packages repo, pick the ones you want, and easily import them into either your Spark shell or your application and go from there. With that, I am happy to answer any questions, and I also have all the slides and demo and data available up on GitHub at the link right there. Questions? Nope. All right. Well, thank you very much.